Yellowstone National Park could be sitting on a time bomb. There is a supervolcano underneath the national treasure.
Right now, in the United States, one of the world's largest volcanoes is gearing up to explode. It's known as the Yellowstone Volcano, and it's not just any regular volcano, it's a supervolcano. If Yellowstone decided to erupt, the results would be devastating. Is there anything we can do to stop it? What does it mean for the world? Join us as we delve into how it's gotten bad. Thousands of earthquakes at Yellowstone, and 100,000s are fleeing their homes. The anonymous group strike again. In the current era, where digital infiltrations are more prevalent than physical break-ins, the notorious hacker collective known as Anonymous has once again made headlines by accessing highly classified information. This breach serves as a stark prelude, signaling that larger revelations may be forthcoming. Amidst the serene canyons and captivating geysers of Yellowstone Park, a narrative unfolds that transcends its scenic beauty. Yellowstone National Park is a place of immense historical significance and natural splendor, drawing visitors from around the globe. However, beneath its picturesque facade lies an unfolding story of potential peril. Recent disclosures by Anonymous have shed light on a series of perplexing events that have prompted the closure of this iconic park. Typically, Yellowstone experiences a moderate number of earthquakes annually, averaging between 1,500 to 2,500. These tremors are often clustered together over short periods. Yet, in a stark departure from this norm, the region has recently witnessed an alarming surge in seismic activity, with over 340 earthquakes detected within a relatively brief span. This uptick in tremors has raised significant concerns among park officials and geologists alike. What makes these seismic developments particularly disconcerting is the context of Yellowstone's geological makeup. Despite being classified as a dormant volcano, there are ongoing signs of subterranean activity within the park's vast caldera. Even minor volcanic disturbances within this supervolcanic system can potentially culminate in catastrophic consequences. Could these consequences be as large as ending our world as we know it? Let's find out. The nature of these tremors is such that they largely escape human detection, only registering on sensitive seismic instruments. This hidden aspect of the phenomenon underscores the unpredictable nature of volcanic activity. Unlike conventional earthquakes that inhabitants may feel, these subtle tremors remain largely imperceptible until analyzed through advanced monitoring technology. The implication of heightened seismic activity within Yellowstone raises troubling possibilities. The prospect of a major eruption, once considered a remote contingency, now looms ominously. The concept that Yellowstone's volcanic potential could unleash a catastrophic scale is a stark reminder of the Earth's dynamic and sometimes unpredictable nature. As discussions about Yellowstone's seismic activity predominantly take place within scientific circles, it's crucial to recognize the broader implications of these developments and give them closer scrutiny. The possibility of a significant geological event occurring demands a comprehensive response, including intensified monitoring efforts and the development of robust contingency plans. In the meantime, with Yellowstone temporarily closed to the public due to these unsettling revelations, the veil of uncertainty surrounding the park's future underscores the importance of remaining vigilant and prepared. While the spectacle of nature often captivates our senses, the underlying forces at play serve as a poignant reminder of the profound mysteries and potential hazards inherent in our planet. This period of closure presents an opportunity to reflect on the intricate balance between human activity and the natural world, highlighting the importance of understanding and respecting the Earth's geological processes. As we approach this uncertainty, it's crucial to prioritize scientific research and public safety measures to better comprehend and mitigate the potential risks associated with Yellowstone's volcanic activity. By fostering a deeper understanding of these phenomena and their impacts, we can enhance our ability to adapt and respond effectively to future challenges posed by Earth's dynamic environment. The Yellowstone, a supervolcano. Supervolcanoes are geological marvels distinguished by their colossal scale and the potential for cataclysmic eruptions that dwarf typical volcanic events. Unlike conventional volcanoes, supervolcanoes like Yellowstone possess the capability to expel thousands of times more material during eruptions, unleashing immense destructive force. At the heart of Yellowstone's volcanic system lies the Yellowstone caldera, a monumental volcanic feature that typifies a supervolcano. This caldera is a vast, bow-shaped depression formed following a massive volcanic eruption that depletes the underlying magma chamber, causing the ground above to collapse. The ongoing series of smaller earthquakes in the region suggests that the supervolcano may be approaching a critical state, with mounting pressure and seismic activity signaling potential volcanic unrest. Moreover, the dynamic movement of magma beneath the Earth's crust can induce surface deformation, altering the landscape through subtle rises or falls. This deformation is meticulously monitored using advanced techniques such as GPS, providing crucial insights into the underlying volcanic processes. Recent data suggests that significant magma movement and accumulation may be occurring beneath Yellowstone, fueling concerns about potential volcanic activity. The interaction between subsurface magma and surrounding hydrothermal systems further underscores the complexities of Yellowstone's volcanic dynamics. Hydrothermal features like hot springs, geysers, and steam vents are integral components influenced by underlying volcanic activity. An uptick in the temperature or behavior of these hydrothermal systems can serve as indicators of magma intrusion closer to the surface, heightening the potential for volcanic unrest. Effect of eruption on hydrothermal features. The chemistry of hydrothermal fluids within Yellowstone National Park serves as a crucial indicator of the underlying geological processes unfolding beneath the surface. When magma interacts with groundwater or existing hydrothermal fluids, it initiates chemical transformations that can be detected through changes in fluid composition. Notably, heightened levels of certain elements like silica or sulfur compounds within these fluids can signify the introduction of fresh magmatic material into the system. Park officials remain vigilant in monitoring these chemical variations, recognizing them as early warning signs of potential volcanic activity. Despite their proactive efforts, the unpredictable nature of supervolcanoes like Yellowstone underscores the challenge of anticipating sudden and catastrophic eruptions. The movement of magma beneath the Earth's crust can induce significant deformation, impacting hydrothermal features and altering their behavior. The observable rise in geothermal temperatures, particularly in recent years amid fluctuating climate conditions, presents an additional layer of complexity. Researchers in the area have noted a notable increase in temperatures, potentially linked to subsurface magma movements. This thermal disturbance has had discernible effects on iconic geysers renowned for their periodic eruptions, manifesting as alterations in eruption intervals, durations, and intensities. Of particular concern are the gas emissions recorded within Yellowstone. Elevated levels of sulfur compounds, including sulfur dioxide and hydrogen sulfide, have been detected, indicative of ongoing magmatic activity. Hydrogen sulfide, comprising approximately 0.15% of gas emissions, imparts the distinctive rotten egg odor detectable in certain areas of the park, an unmistakable sign of volcanic unrest. Monitoring gas emissions around hydrothermal areas within Yellowstone National Park is a vital component of ongoing volcanic surveillance efforts. These emissions serve as critical indicators of heightened volcanic activity, providing valuable insights even in the absence of detectable seismic tremors. However, it is the seismic activity, specifically the historic eruptions, that truly illuminates the geological significance of Yellowstone's volatile past. The formation of Yellowstone caldera. The Yellowstone caldera, a colossal volcanic feature at the heart of the park, was forged by a series of 3 monumental eruptions spanning over 2.1 million years. Each of these cataclysmic events, the Huckleberry Ridge eruption, the Mesa Falls eruption, and the Lava Creek eruption, left an indelible mark on the landscape and reshaped the region's geological narrative. The Huckleberry Ridge eruption, the earliest of the trio, birthed the Island Park caldera, an immense volcanic crater measuring an astounding 47 miles in length, stretching from Yellowstone into Idaho's Island Park region. This eruption, one of the largest in Earth's history, expelled a staggering 590 cubic miles of volcanic material, dramatically altering the surrounding environment and beyond. The event unfolded in distinct phases over decades, characterized by violent explosions that hurled ash and pyroclastic flows into the atmosphere. Following the Huckleberry Ridge eruption, the Mesa Falls eruption occurred approximately 1.3 million years ago, marking the second major caldera-forming event within the Yellowstone hotspot. This eruption gave rise to the Henry's Fork caldera in Idaho, expelling an estimated 280 cubic miles of volcanic material. Though smaller in scale compared to its predecessor, the Mesa Falls eruption played a pivotal role in shaping the Yellowstone Plateau volcanic field, influencing the region's unique geological formations. The volcanic deposits resulting from these historic eruptions, such as the Mesa Falls Tuff, comprise layers of compacted volcanic ash and rock fragments, forming durable rock formations that endure to this day. These eruptions, while awe-inspiring in their magnitude, also serve as poignant reminders of Yellowstone's dynamic geological history and the ongoing processes that continue to shape the landscape. The result of this expansion is Henry's Fort caldera, which measures around 15.5 miles in width and adds to the massive overall volcanic features in the area. The Lava Creek eruption, occurring approximately 640,000 years ago, marks a pivotal event in the history of the Yellowstone hotspot, a region characterized by intense volcanic activity. Despite its volume being slightly less than earlier eruptions, the Lava Creek eruption remains a formidable testament to the geological forces at play, contributing to the complex landscape we observe today. What if Yellowstone actually erupts? Looking ahead, the prospect of another supervolcano eruption at Yellowstone evokes a sobering scenario of potential chaos. Supervolcano eruptions are fueled by the accumulation of vast magma reservoirs beneath the Earth's crust, exerting immense pressure that can culminate in catastrophic events. Given Yellowstone's geological profile, signs of impending volcanic activity often manifest through increased seismicity, a surge in earthquakes of varying magnitudes, indicative of magma movement and crustal adjustments. Indeed, recent years have witnessed a discernible shift in Yellowstone's volcanic behavior. Since March 2018, the once sporadic eruptions of the renowned Steamboat Geyser have become more frequent, at times occurring weekly, a notable departure from historical patterns documented by researchers. This surge in geyser activity underscores the evolving nature of Yellowstone's volcanic dynamics, prompting close scrutiny from scientists and park officials. The seismic landscape also offers telling insights. In 2014, a notable earthquake registering 4.8 on the Richter scale struck near the Norris Geyser Basin, a region historically devoid of significant seismic activity. This event raised alarms within the scientific community, highlighting the potential implications of increased seismicity in geologically sensitive areas. Imagine the unprecedented impact if Yellowstone were to erupt. Unlike typical volcanic events that are localized, a supervolcano eruption would unfold on a colossal scale, starting with a cataclysmic explosion. This initial blast would release an immense surge of energy, akin to multiple atomic bombs detonating simultaneously, generating a powerful shock wave that radiates outward from the eruption site. As this shock wave travels, it encounters anything in its path, causing a sudden and dramatic increase in pressure that leads to widespread destruction. Even well-built structures could buckle and shatter under extreme forces. Trees, though more flexible, would struggle to withstand the force, with many being uprooted or snapped by the shockwave's impact, a devastating scenario, especially within a national park setting. The aftermath of a supervolcanic eruption introduces a cascade of geological phenomena. A vast expulsion of molten rock, gases, and ash from deep within the Earth's core would mark the onset of such an event. Despite the immense force of the eruption, gravity and the sheer mass of ejected materials may limit their dispersal, leading to localized impacts, but with far-reaching consequences. Among the primary threats posed by such an eruption are lava flows, albeit slow-moving due to their high viscosity. Picture a menacing river of molten rock inching its way across the landscape, posing a persistent danger to anything in its path. While the gradual pace of these lava flows may offer some time for evacuation, the scale and persistence of the eruption could quickly overwhelm efforts to contain or mitigate its impact. Escaping the path of a supervolcanic eruption within a vast area like Yellowstone National Park would be a formidable challenge. The urgency of swift evacuation would be paramount, with residents and visitors alike facing the daunting task of fleeing before the advancing lava consumes large expanses of land. The logistical complexities of such an evacuation underscore the critical importance of preparedness and contingency planning in the face of geological events of this magnitude. Furthermore, the broader environmental impacts of a Yellowstone supereruption would be profound. The injection of vast quantities of ash and gases into the atmosphere could trigger regional and even global climate effects, potentially leading to periods of cooling and disrupted weather patterns. The repercussions of such an event would extend far beyond the immediate vicinity, highlighting the interconnectedness of geological processes and their impact on global systems. The impact of Yellowstone eruption. The reach and impact of lava flows resulting from a supervolcanic eruption at Yellowstone are influenced by several critical factors, including terrain characteristics, cooling processes, and the sheer scale of the eruption event. Generally, these lava flows would extend to a radius of approximately 25 miles from the eruption source. Despite this limited distance, the extreme heat emitted by the lava, often exceeding 1,832 degrees Fahrenheit, poses a significant and far-reaching threat. The intense heat generated by the advancing lava poses risks not only to individuals in the immediate vicinity, but also to the entire infrastructure of Yellowstone National Park and nearby structures. Buildings and other infrastructure within the potential path of the lava flows would be at grave risk. Combustible materials could ignite upon exposure to extreme temperatures, while the sheer force of the advancing lava could cause structural damage or complete destruction, resulting in extensive financial losses estimated in the thousands to millions of dollars. Another critical aspect often overlooked is the profound impact of lava flows on surrounding vegetation during a supervolcanic eruption at Yellowstone. The extreme heat emanating from the advancing lava would pose a grave threat to plant life, causing vegetation to ignite and burn, further contributing to hazardous conditions. The high temperatures would incinerate or severely damage any vegetation in the path of the lava, exacerbating ecological challenges. The consequences extend beyond plant life to wildlife inhabiting the affected areas. Many animals would struggle to escape the slow but relentless movement of the lava, leading to habitat loss and direct threats to local ecosystems. The loss of vegetation and habitat, coupled with the dangers posed by advancing lava, would significantly disrupt the delicate balance of local ecosystems, further compounding the ecological impact of a supervolcanic eruption. Moreover, the aftermath of a Yellowstone supereruption would unleash an immense volume of ash and volcanic debris into the atmosphere, a phenomenon with far-reaching consequences. This mixture of fine particles, rocks, and minerals would be propelled high into the sky by the force of the eruption, forming expansive ash clouds that could travel vast distances depending on wind patterns. As these ash clouds disperse over time, they interact with the atmosphere, impacting visibility and atmospheric conditions over extensive regions. The scattering of sunlight by fine ash particles would lead to reduced visibility and hazy skies, affecting transportation, navigation, and everyday activities. The pervasive presence of volcanic ash in the atmosphere could disrupt air travel, impede outdoor activities, and pose respiratory hazards to populations far beyond the immediate vicinity of the eruption site. The far-reaching effects of a supervolcanic eruption extend beyond the immediate vicinity, impacting the literal atmosphere of the Earth and triggering global-scale phenomena. The injection of ash and sulfur particles into the upper atmosphere creates a reflective barrier for sunlight. When sunlight interacts with these particles, a significant portion of it is scattered and reflected back into space, resulting in reduced solar radiation reaching the Earth's surface, a phenomenon known as volcanic winter. This reduction in solar influx initiates a cooling effect on a planetary scale, leading to noticeable decreases in both daytime and nighttime temperatures. The cooling caused by the ash and sulfur particles can induce shifts in weather patterns, influencing atmospheric circulation, prevailing wind patterns, and ocean currents. These alterations in atmospheric dynamics have the potential to disrupt established weather systems and precipitation patterns in regions far from the eruption site. The prolonged reduction in sunlight reaching the Earth's surface can directly impact agricultural productivity. Photosynthesis, the process by which plants convert sunlight into energy, slows down due to reduced light availability. This slowdown in photosynthesis can lead to delayed growth and development of crops, potentially affecting crop yields and harvest timings. The short-term climate changes induced by volcanic particles typically persist for years to decades, illustrating the profound and enduring impact of supervolcanic eruptions on global climate dynamics. Will Yellowstone erupt anytime soon? When considering Yellowstone's eruption history, it's fascinating to note the significant intervals between major eruptions, approximately 725,000 years on average, based on the three most recent super-eruptions. However, it's crucial to recognize that this average is based on limited data points spanning millions of years. Predicting future volcanic activity solely on this average is akin to forecasting the weather with only a few historical data points, inherently unreliable. Volcanoes like Yellowstone don't adhere to predictable schedules. Instead, they operate based on complex geological processes involving the accumulation of magma and shifts in subsurface pressures. The buildup to an eruption depends on a myriad of factors that are difficult to quantify or forecast accurately. Now, addressing the Hollywood-esque notion of Yellowstone erupting cataclysmically and wiping out humanity or North America, it's important to separate fact from fiction. The reality is that most Yellowstone eruptions historically have been more subdued, characterized by lava flows rather than explosive pyroclastic events. While such eruptions can still cause localized devastation and significant disruptions, they are not existential threats on a global scale. What about the current status of Yellowstone's volcanic activity? The Yellowstone Volcano Observatory, YVO, closely monitors the region for any signs of increased activity, including earthquake swarms, ground deformation, and changes in hydrothermal features. While Yellowstone ranks as a high-threat volcanic system according to hazard assessments, this designation primarily reflects the potential hazards associated with the area, not specifically the likelihood of a supereruption. In reality, Yellowstone's ongoing geological activity poses several tangible risks. Hydrothermal features, such as geysers and hot springs, can be unpredictable and hazardous to visitors. The region also experiences frequent small earthquakes, indicative of the dynamic nature of the underlying volcanic system. Despite these risks, it's essential to emphasize that Yellowstone's geological behavior is a topic of ongoing scientific study and scrutiny. The goal is not to predict when the next eruption will occur, but to better understand the complex processes at play and to mitigate potential risks to human safety and infrastructure. So, in conclusion, while Yellowstone is not on the brink of a catastrophic eruption that would threaten humanity's existence, it remains a scientifically intriguing and potentially hazardous geological hotspot. The focus remains on diligent monitoring, research, and public awareness to ensure preparedness and safety in the face of Yellowstone's dynamic natural phenomena. Other infamous eruptions. The eruption of Mount Tambora in Indonesia in 1815 stands out as one of the most powerful volcanic events in recorded history, with far-reaching impacts on climate and society. This massive explosive event ejected a vast quantity of ash, gases, and particles into the atmosphere, forming an extensive ash cloud that ascended into the stratosphere. The cloud contained substantial amounts of sulfur dioxide gas and aerosols, which acted as reflective agents, scattering sunlight and causing a cooling effect on the Earth's surface. The eruption of Mount Tambora in 1815 had far-reaching consequences that reverberated across the globe. Its impact on climate was profound, leading to the infamous Year Without a Summer in 1816. This climatic anomaly was marked by a significant cooling effect in the northern hemisphere, where temperatures plummeted well below normal levels during what should have been warm months. The abrupt drop in temperatures resulted in unexpected frosts and snowfalls in regions accustomed to milder weather, disrupting agriculture and causing widespread crop failures. The consequences were dire, with severe food shortages and famine affecting numerous communities. The agricultural losses were staggering, amplifying the already challenging conditions faced by many populations. The interconnectedness between volcanic activity, climate disruption, and societal impacts became glaringly evident during this period. The eruption of Mount Tambora injected massive amounts of sulfur dioxide into the stratosphere, forming aerosol particles that reflected sunlight and contributed to the cooling of the Earth's surface. As a result, the altered climate patterns triggered by the eruption had cascading effects on agriculture and food production, highlighting the vulnerability of human societies to natural disasters on a global scale. The year without a summer serves as a stark reminder of how intertwined Earth's natural systems are and how disruptions in one part of the world can have far-reaching consequences across continents. A century later, the eruption of Mount Pinatubo in the Philippines in 1991 similarly ranks among the most catastrophic volcanic events of the 20th century. This eruption, too, released substantial amounts of ash, gases, and particles into the atmosphere, including significant quantities of sulfur dioxide gas and aerosols that remained suspended in the stratosphere for an extended period. The aerosols from the Pinatubo eruption contributed to a cooling effect on global temperatures in the subsequent year, 1992. While the cooling effects were notable, they were less extreme compared to those caused by the Tambora eruption. Nevertheless, localized temperature reductions of up to 1 to 2 degrees Celsius were observed in some areas, impacting regional climates and ecosystems. The disruptions caused by the Mount Pinatubo eruption were not limited to climate alone. The widespread scattering of sunlight and cooling effect led to significant impacts on air travel, with operations throughout the region being suspended for months. It took considerable time for air travel services to return to normal, underscoring the broader societal and economic consequences of major volcanic eruptions on modern infrastructure and global connectivity. The impact of volcanic ash extends beyond inconvenience, posing significant health risks, particularly to individuals with respiratory issues such as asthma, chronic obstructive pulmonary disease, or COPD. Inhaling fine ash particles can irritate the respiratory system, leading to breathing difficulties and exacerbating existing health conditions. Considering the recent global pandemic that primarily affected respiratory systems, many people worldwide are already grappling with respiratory problems, and a supervolcanic eruption would exacerbate these health challenges. Furthermore, the settling of volcanic ash can create a host of environmental and structural issues. Accumulated ash on surfaces both indoors and outdoors can range from a thick layer of dust on streets and buildings to more critical structural concerns. Ash infiltration into ventilation systems, air conditioning units, and other mechanical components can cause blockages and reduce the efficiency of these systems, impacting indoor air quality and temperature regulation. Another famous eruption amongst scientists is one that happened millions of years ago, one known as the Graz Landing supereruption. The prelude to the catastrophic event began eons before the eruption itself, with subtle yet significant changes occurring deep within the Earth. Over millennia, immense heat accumulated beneath the planet's crust, gradually melting rock and creating vast chambers filled with a complex mixture of magma, water vapor, and various gases, including carbon dioxide. This subterranean activity led to a slow but steady expansion, exerting increasing pressure on the surrounding rock and terrain. A year before the supereruption at Yellowstone, nature issued a subtle warning, a mere burp that went unnoticed, as there were no interpreters of such signals back then. The alarming processes primarily unfolded beneath the surface, including the release of gas bubbles due to decompression, a phenomenon often associated with specific eruption types. In the lead-up to the eruption, the region experienced a surge in small-scale earthquakes, growing more frequent and intense over time. Ground temperatures in numerous locations rose noticeably, affecting surface lakes and groundwater, which also warmed. Had human eyes been present to witness, they might have observed unusual steam formations in the area, an indication of the underground turmoil. Shortly before the eruption, mounting pressure beneath the surface pushed the ground over the magma chamber upward, forming a dome-shaped uplift. Along the edges of this dome, narrow cracks began to appear, much like the release of pressure from a vigorously shaken soda bottle. As the climactic moment approached, geothermal pools and geysers heated significantly, their chemical composition becoming more acidic than usual. Meanwhile, magma ascended toward the surface, gradually weakening the rock roof of the chamber until it could no longer withstand the pressure, triggering the eruption. In the days leading up to the disaster, the ground experienced subtle yet continuous tremors, intensifying into violent shakes just moments before the eruption commenced with a deafening roar. A colossal column of lava and ash surged into the sky within minutes, followed swiftly by a pyroclastic flow, a lethal mix of semi-solid lava fragments, ash, and scorching gases, moving at hurricane-like speeds and incinerating everything in its path with temperatures exceeding 1,300 degrees F. In the aftermath, the volcano continued to spew ash relentlessly. Volcanic ash, upon inhalation, instantly solidified into glassy particles, proving fatal to most forms of life in the vicinity. Even the mightiest trees succumbed to the weight of this dense substance. Within a matter of days, a thick blanket of ash covered vast territories, its impact reaching beyond the immediate vicinity as it ascended into the stratosphere. The airborne ash particles caused a global cooling effect due to their sulfur-rich composition, resulting in several years of abnormally cold temperatures and the absence of summer across the world. Described by researchers as a colossal natural disaster, the Graz Landing super eruption sterilized the land, wiping out all thriving plant life across a vast expanse. If such an eruption were to occur in modern times, it would blanket entire states like Colorado, Utah, and Wyoming under nearly 3 feet of toxic volcanic ash, causing widespread disruption to life and infrastructure across the nation. Thankfully, scientists assure us that such an apocalyptic scenario is not anticipated in the foreseeable future. However, the geological record serves as a sobering reminder of the immense power and unpredictable nature of Earth's volcanic activity. The potential eruption of Yellowstone as a supervolcano amid existing climate change challenges raises additional concerns. Climate patterns have already shown extremes, with extremely cold winters followed by intense summers. A supervolcanic eruption could exacerbate this variability, further intensifying the greenhouse effect and prolonging periods of cooler temperatures. When the volcanic ash eventually dissipates, the increased greenhouse effect could contribute to even hotter summers, amplifying the impact, particularly in regions near Yellowstone National Park and areas already experiencing high summer temperatures. The cumulative effects of climate change, coupled with the potential consequences of a supervolcanic eruption, present complex challenges for societies worldwide. The world is already struggling to cope with the impacts of climate change, ranging from extreme weather events to disruptions in ecosystems and agriculture. A supervolcanic eruption at Yellowstone would compound these challenges, underscoring the urgent need for proactive measures to mitigate climate-related risks and strengthen resilience at local, regional, and global levels. Addressing these multifaceted challenges requires collaborative efforts across scientific, governmental, and community stakeholders. By prioritizing climate resilience, sustainable development, and adaptive strategies, we can navigate the uncertainties posed by volcanic activity and climate change, ensuring the well-being of present and future generations in the face of evolving environmental challenges. Thanks for watching. Make sure to subscribe to our channel and check out another of our interesting videos before you leave.